So therefore, the conclusion is that although there exists no exact operator in QFT, in QFT, we can construct zero x vector to be given by phi 0 x vector acting on vacuum, which is single particle excitation at t equal to 0 and x. Okay, for non-zero time, phi of x acting on vacuum can be written as, we can use this expression that non-zero time quantum field is a time translation of zero time quantum field. So e to the power translation operator e to the power IHT phi hat 0 x vector e to the power minus IHT acting on vacuum, which is same as e to the power IHT 0 x vector. And therefore it is t comma x vector, and xy causal, if you take the overlap between a such state, so this is x, if you take such state and take the overlap and take the causal overlap, which is defined by the time ordered product of phi hat x phi hat y. So this is, I mean, you would expect that this x comma xy overlap. Now, if you recall that the relativistic worldline theory was a natural construction mainly guided by geometry and symmetry. There was not much room for us to make modifications. They simply followed from logic, and therefore we may expect it to produce causal results, and then and therefore xy is automatically xy as one calculates in the relativistic worldline theory is all automatically causal. So there is no, so recall relativistic relativistic worldline theory was constructed mainly using geometry and symmetry. which means not much room, was naturally which means geometry on symmetry, which means that that is logically followed. So we may expect that x, y overlap calculated in relativistic worldline theory is automatically causal. Now, this is the argument of using some QFT interpretation. Now we will do an explicit calculation. And to verify this claim, so first define Euclidean version of relativistic worldline propagator, which is k bar of x bar minus y bar, by definition is same as k x minus y, with x0 equals minus I x bar 0 and y0 and xi equals x bar I, and so on for y. And then Fourier transform, which is k bar tilde p bar q bar is equal to integral dd x bar by 2 pi to the power d by 2 and dd y by divided by 2 pi to the power d by 2 e to the power minus I p bar dot x bar minus I q bar dot y bar k bar minus y bar. This is a Fourier transform, and then use the result that we had already found. We had already calculated, and once you substitute that result, you get the expression dE 0 to infinity alpha pi I h bar e to the power minus d by 2 e to the power minus I e mu square over alpha h bar integral dd x bar by 2 pi to the power d by 2 dd y bar by 2 pi to the power d by 2 e to the power minus I p bar dot x bar minus I q bar dot y bar times the phase e to the power I by alpha h bar e x bar minus y bar square. Okay, and then weak rotate also the worldline time. If you recall, in our derivation of this result, I mean the real time result, this E came from the S integral. So the action had this lambda. E was the value of lambda, so it was sitting in the integrand of the S integral, and then we rescaled S to make the integrand independent of E. So that's what was done, and therefore, so that S has to be, this S is a time-like parameter, because S is a reparameterization from tau as a proper time. So tau is a time-like parameter. So S is also a time-like parameter. So in order to do Euclideanization, one should also Euclideanize S. And if you follow all of that, then you are basically Euclideanizing E. So weak rotate also worldline time and write E equals minus IU. Then the same expression is given by minus I du 0 to infinity alpha pi h bar u alpha pi h bar u to the power minus d by 2, then e to the power minus u mu square over alpha h bar, and d y bar by 2 pi to the power d, okay, times e to the power minus I q bar dot y bar times j p bar u, where j p bar u is given by the following expression. Okay, so I didn't forget to draw a line. So where j p bar comma u is given by integral d dx bar e to the power minus I p bar dot x bar minus 1 over alpha h bar u x bar minus y bar square. Now, as usual, in order to do this integral, you complete the square and perform the Gaussian integral, and those details are like so after completing the square, you get the following result. It's a bit of algebra. You can do it d dx bar e to the power minus 1 over alpha h bar u x bar minus y bar plus I alpha u by 2 p bar whole square e to the power minus alpha h bar u by 4 p bar square minus I p bar dot y bar. And after doing this is the Gaussian integral, x integral is a Gaussian integral, and the result is alpha pi h bar u to the power d by 2 e to the power minus alpha h bar u by 4 p bar square minus I p bar dot y bar. Then substituting this result back into the Fourier transform of the Euclidean propagator is given by, so J has, so we had this to the power minus d by 2, and j we just calculated, which has the same factor inverse, so that cancel. So you have minus I integral du 0 to infinity e to the power minus u nu square over alpha h bar integral d dy bar by 2 pi to the power d. Okay, then e to the power minus I q bar dot y bar times this factor here, which is e to the power minus alpha h bar u by 4 p bar square minus I p bar dot y bar. So if you do the y bar integral, then this is independent of y bar. Then it will give you a delta function in p plus q, and the rest is the u integral. Which is e to the power minus constant times u, and so the final result is given by, if you do the calculation. So u integral is simple because it is integral e to the power u times a constant. You collect this term, which is linear in u, this term is linear in u. This will give you the delta p plus q, delta function p plus q, and this is e to the power say a times e to the power a times u, which is e to the power a times u divided by a, with u limit being 0 to infinity, and the final result, I'm writing down the final result, is minus I h bar delta p bar plus q bar divided by alpha h bar square by 4 p bar square plus nu square over alpha. So for the final result for the Euclidean propagator, therefore, is this is the Fourier transform. The Euclidean propagator is minus I h bar integral dd p bar by 2 pi to the power d. So you basically substitute this result in here, the inverse transformation of this, and calculate k x minus y, x bar minus y bar. And that result is e to the power I p bar dot x bar minus y bar divided by alpha h bar square by 4 p bar square plus mu square by alpha. And we had earlier calculated nu delta x bar y bar. Recall delta bar x bar minus y bar was I h bar integral so this is minus infinity plus infinity dd p bar over 2 pi to the power d to the I p bar x bar minus y bar divided by p bar square plus m square. Therefore, k bar x bar minus y bar is equal to some phase times delta bar x bar minus y bar, provided we identify the parameters properly, which is alpha is equal to 4 by h bar square and nu square is equal to 4 by h bar square m square. Okay, so that is the result, and also recall that S worldline action was 1 over alpha integral ds 0 to 1 lambda inverse x dot square minus lambda mu square. So this should become 1 over 4 integral ds 0 to 1 lambda inverse h bar x dot square minus 4 lambda m square. So there is this awkward h bar sitting with x dot, but you can but rescale. You can rescale x to h bar x. Then your h bar dependence will disappear, and this will make S h bar independent. But the original path integral for the relativistic worldline theory, if you go back, you will see that only so this is the action. Action we just discussed the action. In the action is quadratic in x dot, and there is no other x dependence anywhere else. So if you rescale x to h bar x, you are just changing the measure by some factor of h bar, which you can always define, by observing the redefinition of this. Right. So redefinition of the path integral measure. What this redefinition actually means is that you don't calculate this type of matrix element, but you calculate the ratio of this matrix element with the vacuum expectation value. And when you change the measure by a constant factor, then the vacuum expectation value also changed by the same factor, and that cancels. This is one way of looking at it. Another way of looking at it, that you always normalize the overall constant to be consistent with the vacuum expectation value to be 1. So that is what I said in the first explanation, that when you have this extra h bar factor, you absorb it into the overall constant. What it means is that you are resetting the overall constant to maintain this. So therefore, there is no unusual appearance of h bar anywhere because of this because of this property of the action, and that establishes the promised relation between the relativistic worldline theory path integral language and the Klein-Gordon theory free massive scalar field in space-time. One is the worldline theory and other is the space-time theory. The connection between these two now is established. So that is the end of today's discussion.